So this example asks you to simplify this system with one resultant force and one resultant moment of one C. So what it asks for is simplify to force resultant at C and M resultant at C. So at the end you get 2. No matter how many loading you have, at the end you get 2 at point C, right? And don't forget, this value, not force, but the moment will change if you change your reference point. Because moment depends on the arm, moment arm. So if you change the reference point, this value will change. So what should I do? Well, before I go to the procedure to find moment, which was break it down, move it, compute the moment, right? I should simplify, get rid of this distributed load. Because this is not intuitive. I want to have a point load acting at some point. So I can do the procedure, I know how to do it before, right? So the procedure for simplifying the distributed load to point load is step 1, find the area, find A, step 2, find centroid, step 3, this find area give you force, value of force, point force. Right? Step 3, you put point force at the centroid. Three steps. So for every area that we have, we do this. Find the area that's going to give you the point, the value of point load. And then you find the centroid. You put that point load as centroid, and then you get rid of this area. Put the point as a centroid and get rid of the distributed load and eliminate the distributed load. Right? So in this particular case, get another card. All right. So step 1, find the area under this load. What's the area? 15 times 800, right? So you replace, this is the centroid. You consider this rectangle, although this shape is complicated, right? But you can always break it down into either rectangle or triangle, because we know what the area is, we know the formula, and we know the centroid, right? So no matter how complicated the shape is in this course, you can always break it down into these 2 cases. For the most general shape that we have curved, we have to do integration. We'll cover that soon, right? So right now, I'll break this into a triangle and a rectangle, right? The area of this guy is 15 times 800. So the value of point force in this case is 15 times 800. Where should I put it? At the centroid. Where is the centroid? Just the middle. So I put the force like that, and this value is just the area, which is 15 times 800. You see that? And I put it at center. What's the distance here? So if this is 15, this is 7.5. Now, eliminate the distributed load. Why? Because we have replaced it with point load. There is no reason to keep this original thing right there. Right? So we just eliminate it. Now, when you practice a lot, you just do it everything you want. You don't change anything. You don't eliminate anything. You don't draw anything. Right? But right now, for this moment, I just want to make this more visible, more readable. So that is equal to the distributed load I have here, the uniform load. Now let's go to this guy. This is a triangle. Step 1, find the area to get the value of point load, the equivalent point load. What's the area? 800 times 15. divided by 2. So it's 400 times 15, right? So the value of point load is, in this case, is 400 times 15. And the step 2, find the centroid. Where is the centroid? For a triangle, if you have a triangle like that, this is base, this is height. The centroid is a point like this that is 1/3 of the height and 1/3 of the base. You can draw this using integration, right? So where is the centroid of this triangle from this base? What's this distance? 5. Thank you. 1/3 of the height. You see, 1/3 of the height, right? So from here to here is 5, right? And the value of the point load is step number 1, the area which we have. So now eliminate it. We'll replace it with a point load. So there is no reason to keep it anymore. So here we go here. This guy too. So we have 2 point load. A non-uniform distributed load will be 2 point loads acting at different points. Now I go back to the question. The question is, simplify these 2 to 1 force and 1 moment at point C. So what's the resultant force? Resultant force, the x component, is simply sum of all x component when you break down all the forces, right? Equal to, what do I get? 0. There is no x component. Resultant force, the y component, sum of all y components. 400 times 15, positive or negative? Negative, thank you. So again, if this is your reference coordinate, xy, this is positive, this is negative, going down, right? Then the next one would be negative 800 times 15. What else? Do I have more force in the y direction? No, that's all, right? What about the moment? Moment resultant with respect to point C, because that's what question is asking for, right? I'm just following whatever question they're asking for. And resultant with respect to point C. Let's just start with this guy. Step 1, break it down. Step 2, move. Step 3, compute the moment. Get the momentum and compute the moment. This is already in the y component, so you don't need to break it down. You go to step 2, move it. It's already perpendicular. You see, you can move it a little bit up, and then this becomes perfectly normal to this distance vector, right? So what's the moment arm? 20. From here to here, which is 15 plus 5 here, 20. So moment arm, step 3 computed. Moment arm times the value of force. What's the value of force? 400 times 15. Positive or negative? Negative. Thank you. We go to this guy. The step 1, break it down. It's already in y. No break. The step 2, move it. Wherever at this point. It's already perpendicular. Step 3, compute the moment. So the moment arm is 7.5 times the value of force. 15,800. Positive or negative? Negative. That's it, right? So this is called a standard simplification. that you end up with one force vector. This is one force vector, although it has two components, but it's just one force vector and one moment vector. And no matter how many force and moments you have on the system, like let's say this building, it has almost infinite number of force and moment loading on the building. From us, from the wind, the distributed load from the wind, right? Because that's all around the building. It's not acting at a particular point, right? The pressure is higher in front of the building. When the wind is going over the building, at the front side, the pressure is higher. But the pressure is different from some other point in the building. So the distributed load is different. And then it comes the load from me, from you. And then it's dead load, the weights, the column, right? The concrete, the weight of the dead load, the weight of the concrete in the column. So it has many forces, right? Applied on the building. But at the end, you end up with one force vector, one moment vector, if you do this procedure, right? So let's do this computation and go the next step in the problem. So grab a calculator. Negative. This is going to be 18J. All right, so that's what I get when I put in the calculator. That's what I got. So now I eliminate these two guys because I simplified them, right? So I eliminate all these things, loading. And I replace, at this point C, with one single force, which is 18K. You see the X component is 0. So we just get the Y component, 18K, and one moment, 210K. And it's negative. See? So, this is the simplified version, the standard simplified form of loading on system. Now we want to get the most simplified form. So we can go one step further and simplify it a little bit more. So what do I get? At the end of the day, I want to get just one single force, not moment and force. I want to get one single force that has the same effect of torque on the system, that I can get rid of this, and replace it with one single force. So how can I do that? Well, get this force, and this is the first time it says you move it sideways, right? Like this way, right? Not a long line of action. So where should I move this such that it can generate this moment implicitly? So I don't need to have this moment right here. So just one force is enough to create this rotational effect too. So where should I move it? Let's say I move it to a distance E. I don't know. That's one of our unknowns. I should find it. I should move it to a distance E, this 18K, such that, so when I move it, I just erase it, right? Because I displaced it. Distance E, such that the moment it generates around this point is equal to 210K. So let's put it in the equation. What's the moment it generates if I move it to distance D?
210 divided by 18.
No, what's the moment this force generate if I move it by D?
210. It's 18 times.
18K, the force times distance D. This should be equal 210K in order to balance the system. So if this is valid, I can immediately erase this moment. This is just extra. We don't need it. We no longer need it. Why? Because this single force by itself can generate this torque itself. So at the end of the day, this is the most simplified form of the system. I have one force and a particular, a specific distance, instead of all the distributed load or distributed moment or whatever, right? So we solve for D. This cancels out with this, so D is equal to 210 over 18. 210 over 18. I forgot, we did this in last class. 210. 11.7. 6667, right? All right, so it means that if you move this force at the distance from point C equal to 11.7, then that single force is equal to the original distributed load. You remember the original distributed load was something like this, right? This was the original distributed load. We did the step one, we replaced the point load. And then we moved all the point load here, right? We get force and moment. And then we move that force to get rid of moment. And this single one, this single 18K that is acting at location 11.7 is equal to all these things. So this is the most simplified form of system, right? All right, now let's go to another example. Use my black one now. This is going to be in this example. Let's do that one more. At the center of this. 2K and 3. 3, 4, 5. So let's say the length of each segment is 2. So length, that's going to be a length of segment is 2 meters, right? And this system is given. Now what I'm asking is replace this complicated loading with one single force vector and one single moment vector at point A. Let's call that point A. So when you see this force, you see this is acting at the middle. So if this is 2, you see the length of this segment is 2, right? So what's the distance? It's 1. Let's assume that these are all at the middle. The one that is applied is either at the end or at the middle. You see? So this length would be 1. This length would be 1, right? Now I want to replace this force and system, moment system. You see, we have a couple moment here with one force vector and one moment vector at point A, right? So what's the first step? Well, you see these oddly distributed loads, right? What do you want to do is to use this procedure to first get rid of the distributed loads and get everything point load, get everything straight, right? And then we know how to handle point loads. Then we do the procedure. Break it down, move it to compute the moment. Right? So let's do that. For this guy, what should I write? So So this is from here to here is 1 meter times 5. So it's 5K. What's the line of action? At the centroid. The step number 2, find the centroid. The centroid is 1/3 of the height. So from here to here is 1/3. Because this is 1/3 of 1 is 1/3. Right? So 1/3 from here. And the value of this force is equal to 5K divided by 2, which is 2.5 K. Right? You see that? So you can erase the red one. Now I keep it, just for you to know how I replace it, right? What about this guy? What should I do with this trapezoidal, you know? The first thing I say, well, I don't know the formula for the centroid of trapezoidal, so I can get the stock, right? Say, well, I don't really know how to do that. And then you go to the appendix, to the test, because I may put some formula, and then you don't find the formula for centroid, and then you get a stock. But look, we can decompose it into, break it down into a triangle and a rectangle. That's this guy. So this area, this load is composed of 2 simple loads, right? 1 rectangle and 1 triangle. So what should I put for the rectangle? The centroid. Where is the centroid of the rectangle? Just at the middle. This is so easy, right? So you put a force here, like that, at the middle. So this distance is just 1 meter, right? If this is 2, see the length of each segment is 2. That distance is 1. So what's the value of force? 1K times 2. So it's 2K. The area, step 1. The area under it is the value of point load. Right? What about this guy? It's 2 times the height. What's the height? 4. You see 5 minus 1 is 4. 4 times 2 divided by 2. So it's just 4K. And the point line of action is right here. So I have a 4K that acts at this distance. What is this distance? 1/3 of 2. The height. You see the height of the triangle is from here to here. So in fact, this distance is 2/3 from here. 1/3 of 2. 2/3. Right? What about this guy? This guy at the center, the force is 2K times 1. So it's going to be 2K, and it goes at the center, and the center of that is half from here. If this is 1, this is half, right? And these 2 guys are so obvious. They're already point load. So you don't need to do this algorithm, but they are point load. They're not distributed load. Right? Now I'm ready to go back and find my resultant force and moment with respect to point A. So let's write it. F resultant X in the X direction. Let's start with this guy. With this. What should I write? 2K times 3/5. Positive or negative? Negative. Now we go to the next one, the X component. Plus 4K times cosine 60. Positive, thank you. Next one. What should I write?
2K times 0.5.
No, we're just doing the
Oh, okay.
force,
Yeah,
not
the force,
the
yeah.
moment. That's right, if we do moments, right? But we're not doing moment. Just simply 2K, positive. We're going this way, right? Now we go to this guy. What about this?
0.
0. What about this?
0.
No x component. You see that?
Mhm.
There is no x component. What about this?
0.
0. This is just a couple moment. So this will add to the moment equation. It has nothing to do with the force equation. It's just a moment. We had in previous classes, even if you put two forces that generate this couple moment, they cancel out. You remember the example we had? 200, negative 200, they cancel out. So has nothing to do with the force equation. Next one. This one. What should I do? Well, if that's 20 degree and this is normal, this side, then we can say this one is 20 degree. How do you do that?
Angle operation.
Angle operation, right? So I would say, if you imagine we can bring it back here, if this becomes 0, that becomes 0. The amount you deflect this is the amount this deflects. So you can immediately find this 20 degree, right? But you can always do angle computation and find it. It's just something easy to do that, right? So then the x component would be
Negative 5 cosine 20.
negative
2.5.
right? We're not doing anything with the distributed load. This is in fact nothing here. Instead of erasing it, because we replaced it with the blue. We replace the red with the blue. So instead of erasing it, I will keep it so you can see which one is replaced with what. So 2.5 times
Cosine 20.
2.5 cosine 20 degree. Positive or negative?
Negative.
Negative. What else? That's it, right? Now let's go to the resultant force in the y direction. Let's start with this. Now you tell me what to write. Let's start from left to right.
2 times
So, yeah.
2k, 4/5, positive or negative?
Positive.
Positive there. 4k sine 60, 0. Then you create come here plus 4k plus 2k.
Okay.
Right? This has nothing to do with force, couple moment. Skip it. Then here, plus 2.5k times
Sine 20.
sine 20 degree. Moment resultant about point A. Now what should I write? This is a little bit lengthier than that. So let's start with this guy. This one has an angle. Step number 1, break it down. Step number 2, move. Step number 3, get the moment arm and compute the moment, force and moment arm. So if you break it down, it has an x component. What's the moment of x component?
0.
0. It goes through that point, right? So I only do the y component. So what should I write? This distance, which is 1, times
2k.
2k
4/5.
4/5. Positive or negative?
Positive.
Thank you. Like that. All right? Now we go to the next one. Now just tell me what should I write with it. 4k sine 60 times 2, positive or negative?
Positive.
Positive. Now let's go to this guy. I'm talking about the blue. I'm talking about the blue one. What should I do with respect to point A? Move it, because this is not normal to that, right? This angle is not normal. You see this angle here? Move it. Where should I move it? Back to the left. So the moment arm is from here to here. So what's the moment arm?
1.5.
if this is 2, 2 minus half,
Half.
so it's 1.5 times,
2.
don't forget the K, 2K. Because that K means 1,000, right? Positive or negative? Positive, thank you. Now let's go to this guy. What should I do with this? Move it. Where? Up. So the moment arm is 2 plus 2/3. So I write here 2 plus 2/3 times 1K. Positive or negative? Positive. You see that? So I'm talking about this guy. This one is not perpendicular to this, right? So you have to move it. Now moment arm become here, which is 2, because the length of this segment is 2. Plus this distance. This distance is 2 over 3.
So why didn't we do a y component for the 1, 4?
Which one?
For the 2K on the block?
This one is this 1 or 4?
No, right here. So on the force that we just did earlier, the 1.5 times 2K, why didn't we do a y component for that?
Which one are you talking about? This one?
That one, yes.
Well, this one, if you move it here,
Yeah, I guess.
you see, don't forget the step 1, move. If it's, because this is not normal to this point, right? If you move it, then it becomes perfectly perpendicular. So this is moment arm, this force. Now, is this 4?
That's a 4. That's 4.
That's a 4, I erased it. So if this is 4, yeah, my finger sometimes makes problem. So if that's 4, move it here. So the moment arm is 2 plus 2/3 times 4. Okay, positive or negative? Positive, right? Now go to the next one. Go to this one. Where should I move it? Up. So what's the moment arm? 3 times
2K.
2K. Positive or negative?
Positive.
What about this guy?
0.
It's just 2 plus 2. 2 kilonewtons.
2 negative. You see? Negative 2. There is no moment arm. This is a moment. You don't need to find the moment arm. You don't need to move it because it's already a moment. If it was a force, you should have moved it to get a moment, right? So just add it. So 2K negative because it's going this way, right? Now go to the next one. This guy has some angle, it's not straight, like this. So step 1, break it down. Step number 2, move each component. Step number 3, get the moment arm and complete the moment. So if you break it down, this one, you get x component, which is 2.5 cosine 20 degree, and then there is a y component going up, and this is 2.5k sine 20. Alright? So let's grab the x component. Where should I move it?
Back.
All the way back here. So what's the moment arm?
1 or 2 plus 2. That's what that is.
Interesting. How can I find the moment arm? Look, move it here, right? You move it all the way here, and then you put it here, and this becomes orthogonal. So this is a moment arm. So how can I find this distance? Well, from here to here is what? 2, right? If I can subtract this component from 2, from here to here, right? From here to here. If I subtract this from 2, then I get this little guy here, right?
Mm-hmm.
So 2 minus, from here to here, 2 minus this one. This one is whatever you have to here times cosine 20. So what do you have from here to here? 2 minus, this distance is 1/3, right? So 2 minus 1/3 cosine 20. Now this is moment arm. You see it's a little bit long, but you can imagine what's going on, right? So here to here is 2. The first 2 you see is from here to here, right? And I need to subtract by this value. And what is this value? This value is from here to here, which is this length, which is 2 minus 1/3 cosine 20. So that's the total moment arm. You can do it step by step. You can compute this guy, this length first, put it in the calculator. It's going to be this length, which is 2 minus 1/3 cosine 20, and put the numerical value here, and then you can say 2 minus this value is the moment arm. Right? Again, if you don't get it, you need to practice it more at home. At one point you start clicking. So okay, now I know. Right? Moment arm times the value of force component. What's the value of force component? 2.5 K cosine 20. Positive or negative? Negative. Now let's go to this guy. Now we have quiz bonus. One quiz bonus. If you can tell me what's the moment arm for the vertical component. I count 10 and then I do it myself. 1, 2, 3, 4, 5. Yeah.
Is it 2.5K sine of 20 times?
Now I'm just asking about the arm, just the arm.
4 minus 2 sine of 20?
No.
4 plus?
Yeah. Unfortunately, I just feel bonus is just first right. So, but next time we definitely have one to. So 4 plus. So why 4? Why 4?
Because you got 2 and 2.
Yeah, look, I want to find this distance from here all the way to here, right? So from here to here is what? 2. Because the length of each segment is 2. From here to here is what? 2. So from here to here is 4. Plus this segment here. So what's the distance? If this is 2, if this is 2 minus 1/3, then it's 2 minus 1/3 times sine 20. 4 plus 2 minus 1/3 sine 20. That still wasn't correct. You see? Because here, from here to here is what? 2, the entire segment minus 1/3. Right? Times sine 20. Added to the first 4. Right, the shift. So this is moment arm times the value of component. What's the value of component? 2.5 K sine 20 degrees. Now you put it in a calculator, and then at the end you get rid of all these things here. Because you simplify, right? You erase all these things, and you replace it with one force and one moment at point A. So you just erase everything here. Makes your system very more readable. And then at point A, you have FRX, right? FR, resultant Y component, and resultant moment at point A. And this by itself is just one vector. This is one vector, right? F resultant. So you have one vector, one moment. The numerical value is given there. Now, if I ask you just simplify to one force, what do you do? Yeah, you shift this in a way like this way, not a one line of action, sideways, right? This way, such that this distance times the force creates this moment resultant. So at the end, you only have one force acting at a particular location, right? Then you can find that distance. All right? That's the most simplified form of the system. All right.